This chapter addresses how to evaluate retrieval augmented generation. The RAG pipeline should be decomposed into separate stages for evaluation. Consider a resident asking why a property tax estimate increased and which county rule supports it. The assistant responds confidently, but cites a neighborhood maintenance policy and an outdated listing description. Although the generation is fluent and the citations are real, the answer is wrong because Retrieval supplied the wrong evidence. A prompt change cannot reliably repair evidence that was missing or ranked incorrectly. The practical consequence is to evaluate the path to the answer, not only the final answer. Query construction, retrieval, re-ranking, context packing, generation, and citation behavior are separate stages, each with separate inputs, outputs, failure modes, and success criteria. The pipeline can be evaluated as a set of contracts. For the cumulative real estate assistant, represent one request as a trace with immutable records at each boundary. At query construction, record the user message and conversation state as inputs, then capture the search query, filters, rewritten query, and extracted entities. Ask whether the system preserved property tax estimate and the relevant jurisdiction. At retrieval, record the query, index, and filters, along with candidate document or chunk IDs, scores, and metadata. Ask whether the governing tax document was retrieved at all. At re-ranking, record the query and candidates, plus the ordered candidates and re-ranker scores. Ask whether the authoritative tax rule was placed ahead of merely similar text. At context packing, record the ordered candidates and token budget, together with the final context, included and omitted IDs and ordering. Ask whether answerable evidence survived truncation and formatting. At generation, record the user request and pack context, along with the answer, claims, citation links, and refusal or uncertainty markers. Ask whether each material claim follows from the supplied evidence. At every boundary, record the raw input and output, version identifiers, timestamps, and configuration. The trace should allow an engineer to reconstruct which query, index snapshot, ranking model, chunking scheme, context budget, and prompt produce the response. Logging only the final answer hides whether a document was never found or was found but ignored. The pipeline diagram is deferred, not complete. Created at assets/fig 08-01. RAG, pipeline.svg, retain the accessible text alternative, caption at figure 8.1. Testable contracts and evaluators across the RAG pipeline. Record the chapter team or any adapted source attribution, and verify labels, directionality, arrow destinations, evaluator placement, readability, and a non-color alternative before publication. Conversation state and the user message enter query construction, which produces a query, filters, and entities. Retrieval produces candidate IDs and scores. Re-ranking produces ordered evidence. Context packing produces final context and omissions. Generation produces claims, an answer, and citations. Evaluators inspect every boundary and the final response, testing each transition and the artifacts it produces. Trace the tax question through each pipeline stage. Assume the county is known from the conversation and the query becomes property tax estimate increase county assessment rule. The wording may be reasonable, but evaluation must check whether it preserves the requested explanation, the applicable jurisdiction, and support from a rule. Dropping the county or replacing assessment rule with tax rate can retrieve plausible but inapplicable material. The retriever returns a current county assessment policy page, a neighborhood FAQ about annual fees, and an older tax rate explainer. Retrieval success means the relevant assessment policy chunk is present, not that it ranks first, is readable, or is sufficient. Record document IDs, chunk boundaries, dates or versions when available, and retrieval scores. Hit rate shows whether evidence entered the set, but not whether the set supports a defensible answer. Here, the older explainer outranks the current policy because its wording resembles the query more closely. Re-ranking evaluation should check whether the relevant item reaches an acceptable rank and whether authority, jurisdiction, and temporal applicability affect ordering. Similarity is not validity. A less similar current county rule may be more useful than a highly similar general explanation. Context packing creates another failure boundary. Filling the budget with the first-ranked chunks can truncate or displace the current policy or separate it from the condition, limiting its applicability. Record the final context, its order, included IDs, and omitted IDs. Fitting the context is not enough. It must retain the evidence required for the requested claims without burying or corrupting it. A bounded answer may say that the estimate increased because the county reassessed the property under the cited assessment rule, while distinguishing an assessment change from a tax rate change and stating when the documents do not establish which occurred. Citation evaluation is separate from factual support. A genuine document may not entail the claim, apply to the right jurisdiction, or include the condition that makes the claim true. After the response is produced, inspect the trace. For the tax question, it should show the issued query, the 3 return candidates, each rank, the policy text that survived packing, and the exact claims linked to citations. If the current county rule never entered retrieval, investigate indexing, query construction, filters, or retrieval depth. If it appeared but ranked below an outdated explainer, investigate re-ranking or authority features. If it ranked first but was omitted from context, investigate packing. If it was packed but the answer cited the wrong document, investigate generation or citation selection. The trace supports diagnosis instead of guessing from fluency. The goal is to find where the failure began, not merely describe its final symptom. Errors move forward through the stages. Losing jurisdiction during query construction can produce candidates from the wrong county. Retrieval failure leaves re-ranking with nothing to rescue. Poor ranking can make packing omit the only authoritative chunk. Packing can retain the right document while removing a qualifying exception. Generation may then misread, overextend, or accurately summarize what remains. Thus, a final hallucination can be the visible endpoint of an earlier contract violation. There are 2 kinds of success. Component success is local. Query construction preserves intent. Retrieval includes relevant evidence. Re-ranking orders it appropriately. Packing retains sufficient support, and generation makes only supported claims with usable citations. End-to-end success is global. A realistic user question receives an accurate, sufficiently supported, jurisdiction-appropriate answer, or an appropriate uncertainty response. A system can pass one definition and fail the other. Retrieval may have excellent coverage while generation cites the wrong chunk, while a capable generator may answer a few easy questions despite systematic retrieval gaps. Component success must be evaluated at the requested claim level. Retrieval may find topically relevant material, but fail sufficiency if it lacks the needed rate, date, exception, or jurisdiction. Re-ranking may place a relevant item first, yet still fail, by placing an obsolete rule ahead of a current one. Generation may be fluent and include citations, but fail when those citations do not support the material claims. These distinctions keep one aggregate score from hiding the first failed contract. Consider the boundary case of a user asking for the tax rate in 2019. The current assessment policy page may be authoritative today, but irrelevant to that question. Relevance depends on time, jurisdiction, and requested level of detail. An evaluation set that labels every current policy page as correct can reward the wrong behavior. The same caution applies to listing and neighborhood knowledge. A document can be authoritative for one question and irrelevant for another. Use the diagnostic artifact to guide the engineering decision. Then compare the resulting configurations systematically. Update the cumulative repository with a RAG trace schema, stage-level fixtures, and an experiment matrix. Each matrix row should vary one meaningful choice, such as query rewriting, chunking, retrieval depth, re-ranking, packing, or a generation policy, while retaining quality, latency, and cost observations. The trace schema makes the tax example diagnosable, and the matrix makes configurations comparable. Add the deferred pipeline visual as assets /fig 08-01 rag pipeline.svg with its specified caption, accessible text alternative, ownership or attribution record, and verification notes. Before publication, verify the visuals labels, directionality, ownership, adaptation permission, attribution, and accessibility. Do not rely on color alone. A useful trace carries the user message, the conversation-derived county, document, and chunk identifiers, available source versions or dates, retrieval and re-ranking scores, packing omissions, generated claims, citation targets, and uncertainty markers. This shared structure supports comparisons across listing, policy, and neighborhood knowledge questions while respecting differences in source relevance and authority. Evaluation spans several roles. AI engineering instruments and debugs the chain. Evaluation engineering maintains relevance and support labels. ML platform engineering preserves index and model version lineage. Product engineering defines acceptable outcomes. And safety engineering checks uncertainty, jurisdiction, and policy boundaries. The shared skill is locating the first failed contract, not selecting a fashionable retriever. Small or synthetic question sets may miss spelling variation, multilingual requests, changing policies, and adversarial queries. Human labels may disagree, and an LLM-Judge does not prove correctness or private reasoning. Stage improvements can coexist with worse end-to-end latency, cost, duplicated context, or confusing citations. Leakage, inconsistent timestamps, incomplete multi-hop labels, and overrepresented easy queries can distort results. These measurements can identify a configuration for controlled testing, but cannot establish legal or tax advice, universal factual correctness, or production safety. Evaluation can fail when the repository is incomplete or contradictory, jurisdiction is unknown, policy changes are unversioned, or required facts are unavailable. A low score does not identify one component without additional labels and trace review, while a high score on a narrow benchmark does not establish robustness to new counties, document formats, or changing rules. The evidence supports choosing what to test or repair next, not presenting uncertain property tax interpretations as professional advice or treating citation presence as proof of claim correctness. Run the experiment grid. Inspect component and end-to-end evidence, and select a configuration only when quality gains remain acceptable alongside latency and cost. Keep query construction, retrieval, re-ranking, packing, and generation as separate testable stages. Record inputs and outputs at every boundary, and use the trace to identify where an answer became unsupported. The next section establishes retrieval ground truth for evaluation. Labeling 100 queries can expose a problem that prompting cannot fix. The assistant may produce a hallucinated answer that is the best possible answer given the documents it retrieved. For example, an answer about short-term rental permission may sound fluent even when retrieval returned an outdated neighborhood summary and an unrelated listing. Before blaming generation, determine whether the retrieved set contained the evidence required to answer. Define the evaluation from the question, not from an individual chunk. Retrieval ground truth links a realistic query to documents or chunks that could support a correct answer. It defines the retrieval contract without requiring every relevant passage to be quoted. Each case includes the query, its scenario, and, where relevant, jurisdiction, the knowledge base snapshot in time, and judgments about candidate documents. Production-derived queries capture abbreviations, incomplete context, spelling variation, and follow-up references, but they require sanitization, permission, privacy review, and representativeness review. Expert-authored queries cover gaps, such as policy edge cases, conflicting listing facts, neighborhood questions, and authority or effective date dependencies. Recording each query source helps identify a benchmark dominated by polish tests or one narrow population. For the initial exercise, label relevant policy and listing chunks for 100 queries. For a question about keeping a large dog at 14, Cedar Lane, supporting evidence might include the listing's pet terms, a building policy, and current association rules when authority is delegated. Record document and chunk identifiers, relevance grades, and an adjudication note when reviewers disagree. Binary relevant or not relevant is often too coarse. Distinguish direct support, partial or contextual support, and irrelevant or misleading material. A current, directly applicable pet policy can be highly relevant, while a general neighborhood page may be weakly relevant and an old listing description may be historically relevant but unsafe for a current answer. Define the grades in the annotation guide and apply them consistently. Relevance judgments must preserve the conditions under which the evidence was considered useful. For every judgment, record whether the document was public, tenant, or agent-restricted or otherwise unavailable in the evaluated user context. A document may be semantically perfect but still invalid as a retrieval target when the application cannot expose it. Access rules belong in ground truth, so retrieval quality does not reward evidence the evaluated assistant is not legitimately allowed to use. Metrics should therefore distinguish semantic relevance from authorized usability. Record publication time, effective date, expiration or supersession status, and a knowledge-based snapshot used for labeling. A superseded policy may explain a historical answer, but should not receive the same grade as the current policy for a present tense query. When freshness is uncertain, mark that uncertainty instead of silently treating the document as current. The snapshot must be an explicit evaluation boundary, not only a label. Store its materialization instant using a time zone-aware UTC timestamp and reject any evaluation time later than that instant. An older time within the snapshot's available history may be evaluated, but evaluation must never silently go beyond the named snapshot. After metadata is added, the 100 query artifact records queries, CRELs, access conditions, freshness, snapshot time, and adjudication. This lets candidate retrievers and re-rankers be compared against the same boundary and makes failures inspectable, including missing accessible evidence, outdated versions, weak context outranking direct policy, or evidence buried below the context limit. Make the labels useful at more than one stage. Ground truth should support multiple relevant documents and graded relevance because different stages answer different questions. Initial retrieval may need broad recall. Did it return any acceptable evidence among its top results? Re-ranking asks whether the strongest evidence moved upward. Context assembly asks whether enough complementary evidence survived deduplication and limits. Citation evaluation later asks whether the generated claim is actually supported by the selected passage. These are related measurements, not interchangeable verdicts. A small boundary case prevents overgeneralization. Suppose a query asks for the nearest public park to a listing. Two neighborhood documents may both be valid sources, while a listing's private agent note is inaccessible and must not count for that evaluated user context, even if it contains the shortest answer. Conversely, for a question about a specific property's HOA restriction, several general neighborhood pages should not be labeled equivalent to the property's governing policy. Relevance is query-dependent, permission-dependent, and sometimes time-dependent. The labels support a decision about retrieval and ranking configurations. Which system finds acceptable evidence under the declared access and snapshot conditions with tolerable latency and cost. They cannot establish that the underlying policy is legally correct, that a listing is still available, or that a generated answer faithfully uses the evidence. They also do not eliminate annotator disagreement, distribution shift, multilingual coverage gaps, adversarial queries, or errors in the source corpus. An LLM-judge's rationale is not proof of correctness or observable private reasoning. Disputed cases require human review or authoritative domain review. Keep the contract executable. Store the retrieval evaluation contract in a typed, serializable shared schema rather than a spreadsheet. Eval case, CREL, and relevance should be canonical definitions in the shared schema module, such as schemas /retrieval_eval.py when no such module exists. Later sections should import and extend them instead of creating parallel local types. The durable core example uses only the Python standard library and deterministic assertions. Provider-specific adapters can convert results into these structures without changing the labels. Its synthetic fixture dates and explicit UTC snapshot contract make the temporal boundary executable. This module defines the typed retrieval evaluation contract and executes the access, relevance, and UTC snapshot boundary. It declares graded relevance values, stores each CREL's document, chunk, access, and temporal fields, and stores eval case metadata and CRELs. Eval case validation rejects non-time zone-aware or non-UTC snapshot and CREL times. Eligible underscore CRELs rejects a non-UTC as underscore a value or one later than the snapshot, then retains accessible, temporally eligible CRELs whose relevance is above irrelevant. Build underscore fixture supplies the case in CRELs. The main block checks the two eligible supporting chunks, checks rejection of a post-snapshot evaluation, and prints the case identifier and eligible count. The relevance grade separates direct from merely contextual evidence. Accessibility prevents an unauthorized passage from becoming a retrieval success. Snapshot underscore at defines the temporal boundary, while effective and superseded timestamps support reproducible evaluation. The checks require time zone-aware UTC comparisons. The assertions show that an inaccessible but semantically relevant agent node is excluded and that a later evaluation cannot silently use the case. It shows that exactly two supporting chunks are eligible for Q001. At the snapshot time, two accessible chunks support the query, while the restricted direct chunk does not count for this user context. A production repository should add schema validation, annotation guide versioning, duplicate label checks, adjudicator identity controls, historical supersession window tests, malformed timestamp tests, and dependency pinning with reruns when adapters are introduced. Later sections should import the canonical shared contract and extend it only when their stage requires additional fields, rather than creating a parallel representation. This artifact is useful in daily work. Evaluation engineers maintain CRELs and adjudications. AI engineers inspect missed evidence. Platform engineers preserve index and snapshot lineage. Product engineers define acceptable user context rules. And safety engineers review access, freshness, and domain boundaries. The next step is not to manufacture unlimited labels. Coverage should expand carefully while tracking where synthetic queries may introduce their own bias. The takeaway is operational. Map realistic queries to all relevant, accessible, and appropriately current chunks or documents, with grades and provenance. Then use that ground truth to decide whether retrieval or re-ranking deserves the next experiment, while keeping separate the later questions of sufficiency, citation support, and answer correctness. Generate and filter synthetic queries. A synthetic question such as "Can a buyer keep a dog in Cedar Court?" may retrieve the wrong condominium policy and still receive a fluent, apparently well-supported answer. If Cedar Court permits dogs only under a weight limit, while Cedar Heights prohibits them entirely, a generator that produces only easy, distinctive questions will make the retriever look better than it is. Synthetic evaluation data must increase coverage without erasing the ambiguities and near misses that real users create. Start with question families, not unlimited paraphrases. Synthetic generation is most useful after retrieval ground truth exists. Relevant, accessible chunks can then be turned into a broader set of testable user intents. Record each question, its answer target, supporting and distractor chunk identifiers and labels, question type, generator version, corpus snapshot, prompt or template version, random seed, filter version, and review status. The benchmark should cover multiple distinct ways of testing retrieval and evidence use. Fact questions ask for one supported attribute, such as the maximum dog weight allowed at Cedar Court. Comparison questions require distinguishing similar records, such as how Cedar Court and Cedar Heights differ on dog restrictions. Multi-hop questions require joining evidence, such as determining whether a buyer at Cedar Court can keep a dog and what application must be submitted before move-in. In a condominium policy scenario, a fact question tests whether the policy chunk can be found. A comparison question tests whether the retriever confuses two similarly worded policies. A multi-hop question tests whether it can assemble the pet rule from one chunk and the application procedure from another without silently substituting a neighboring building's process. Stratify generation by source type, listing, policy, and neighborhood knowledge, and by attributes such as dates, exceptions, negation, access scope, and required actions. Maintain quotas, sample seeds, and a human-reviewed slice instead of letting the generator choose the distribution entirely. For a small fixture, use deterministic configuration, record the seed and quotas, and fail with a useful error when required inputs are absent. Use similar chunks to test whether retrieval distinguishes near matches rather than confusing them. Easy negatives are insufficient because a random chunk from a distant neighborhood is unlikely to challenge retrieval. Hard distractors should be plausible competitors, such as a similar neighboring policy, a superseded rule, or an accessible policy resembling a private note. They test whether the system selects the correct evidence, not whether the answer is false. Each generated record should label candidates as support, distractor, superseded, or inaccessible, while preserving the reason for each label. Comparison questions may have multiple supporting chunks, whereas fact questions may have one. Matching wording is not enough for a private note to count as retrieval success, and a superseded policy is not correct evidence when a newer policy is effective. Keeping labels in the record allows later recall and precision calculations to separate relevant evidence from realistic noise. Return to the case. A question asking whether Cedar Court allows dogs should include Cedar Heights' nearly identical restriction as a distractor, but the answer target must identify the Cedar Court policy and its effective date. A question asking for the rule, without naming a property, is underspecified. It belongs in a realism rejection queue rather than in the scored set. Filter for support, realism, and bias. Synthetic records need two different validations. Support validation asks whether the proposed answer follows from the cited source chunks and whether every material claim has support. Realism validation asks whether a person would plausibly ask the question, whether its wording is unambiguous enough to score, and whether it reflects the intended user population and task mix. A strong filter therefore checks. 1. Every answer-bearing claim has at least one accessible supporting chunk. 2. the cited chunk actually contains the necessary fact, rather than merely sharing vocabulary. 3. The answer does not combine incompatible dates, properties, or policy versions. 4. The question has a determinate answer under the evaluation snapshot. 5. The record does not reveal private or production-derived personal information. 6. The collection is not dominated by one generator's phrasing, one property, or one easy question family. Use a Q rather than an irrevocable pass/fail decision. Records can be marked accepted, needs_review, rejected_unsupported, rejected_ambiguous, or rejected_sensitive. A model-based judge may help prioritize review, but its rationale is not proof of correctness. Human adjudication remains necessary for policy interpretation, access boundaries, and domain-sensitive examples. Real estate examples also require review for privacy, representativeness, and fair housing implications. Synthetic data does not automatically remove those risks. A small boundary case prevents overgeneralization. If a policy chunk says dogs are permitted, a generated answer that adds a weight limit is unsupported unless another accessible chunk supplies that limit. Conversely, a multi-hop question may require 2 chunks, but it should be rejected if the second chunk belongs to a different condominium and the generator has silently merged them. The filter below represents answer-bearing claims explicitly, so changing the answer text or its expected claims cannot bypass validation through a record ID exception. It also rejects inaccessible support, conflicting source versions, ambiguous questions, sensitive records, and duplicate questions in a deterministic way. Preserve lineage as part of the evaluation data. Every record should carry the corpus snapshot, source chunk IDs, source labels, generator configuration, generator version, random seed where applicable, prompt or template version, filter version, and adjudication status. Candidate labels should preserve whether each chunk is support, a distractor, superseded, or inaccessible, together with a reason. This makes a failure diagnosable. A changed answer may result from a new corpus, a new generator, a new filter, or a changed annotation decision. Without lineage, those causes collapse into an unhelpful benchmark moved. The section artifact is a deterministic synthetic QA generator and filtering queue. It creates fact, comparison, and multi-hop records from a small condominium fixture, includes same property and neighboring property distractors, and rejects an unsupported answer. In the cumulative real estate assistant, this changes the evaluation dataset artifact, not the retriever or the answer prompt. The next section can then measure recall and precision against these accepted supporting and distractor chunks. This code defines a deterministic synthetic evaluation contract and filters generated records. It represents chunks, candidate labels, record kinds, adjudication statuses, expected claims, and lineage fields. Generation requires 3 named fixture chunks, creates fact, comparison, multi-hop, and unsupported records, and records the corpus snapshot, generator settings, prompt template version, seed, and filter version. Filtering clears prior reasons, normalizes questions, checks duplicates and empty content, verifies accessible support, rejects sensitive records, checks property and source version consistency, and requires every expected claim to occur in an accessible supporting chunk. The fixture text must include the property names used as expected claims. Otherwise, Q001 and Q002 are rejected by the literal claim, checked despite the assertions requiring acceptance. Duplicate handling and ambiguity handling must also match the stated rejection behavior. The code keeps generation deterministic and side effect free, uses explicit source identifiers and labels, and separates generation from filtering so later repositories can replace the fixture with shared schemas and provider adapters without changing the data contract. Underscore require underscore chunks turns a missing fixture into an explicit configuration error rather than an unhandled key error. Expected claims provide the small deterministic support contract. Every claim must occur in at least one accessible cited chunk. That is deliberately narrower than open-ended natural language entailment, but it is a real reusable check and is not tied to Q004. The candidate structure records support, distractor, superseded, and inaccessible labels even when this fixture does not instantiate every label. Expected output after the fixture text and filtering behavior are corrected is Q001, accepted, Q002, accepted, Q003, accepted, Q004, rejected or unsupported. The assertion also verifies provenance and candidate labeling. The fixture demonstrates the required artifact. It does not implement arbitrary question synthesis, semantic entailment, statistical balance estimation, or human adjudication. Those are explicit production extensions, add schema validation, near duplicate detection, quota and generator dominance reports, superseded version checks, privacy classifiers, snapshot and prompt hashes, and human review controls around this contract. A production source stratification adapter should select listing, policy, and neighborhood chunks under configured quotas and use the recorded seed for reproducibility. Rerun the example in a clean environment with the repository's pinned Python version and lock file. Do not connect this artifact directly to email, browser, database, or other consequential tools. Use sandboxed fixtures. This evidence supports a bounded decision, whether a retrieval configuration can find designated support while resisting realistic, similar distractors. It cannot establish that synthetic questions represent all users, prove answer correctness for unseen policies, or replace production monitoring and human review. It can also fail when source chunks are incomplete, labels are wrong, policy versions are unresolved, claim extraction is too literal, or the generator systematically avoids ambiguous language. The right response is not to inflate the dataset blindly, but to inspect rejected and missed cases, add targeted human-authored examples, and rerun the generation and filtering versions together. Fair housing and policy implications remain review requirements, not conclusions established by this fixture. The artifact serves different operational roles: regression testing, evaluation review, lineage-preserving dataset construction, and inspection of access, privacy, and domain boundaries. Coverage should scale by question family and source strata. Hard distractors should be explicit, support should be validated separately from realism, and lineage should explain benchmark changes before measuring recall and precision at K. Recall and precision at K. In the property policy example, the question concerns keeping a service animal, but the 5 retrieved chunks discuss pet deposits, parking rules, or another property. The generator answers fluently from those documents, yet the result remains unusable because the retrieved evidence does not address the question. This determines the debugging order. First, measure whether the candidate set contains the needed evidence. Then measure how much irrelevant material was included. A prompt change cannot recover a policy clause that retrieval already discarded. The comparison with 2 relevant chunks among 5 is a separate improved run, not a contradiction of the initial failure. Relevance is a labeled relationship. For a query Q, R_Q is the set of documents or chunks judged relevant to answering it. The value K is the number of ranked results inspected, so top 5 means K equals 5 regardless of index size. Relevance must fit the task rather than being inferred from textual similarity alone. A chunk about pets may not address an assistance animal accommodation, while a policy appendix may be decisive despite sharing few words. The synthetic query artifact becomes a retrieval evaluation fixture. Each record needs a stable query identifier, source version information, and a relevance judgment or CREL style mapping to acceptable chunks. For ambiguous questions, retain the judgment rationale or adjudication status instead of silently making uncertainty binary. When a source policy changes, evaluate the query against the version the assistant was expected to use. For the first k results in the retrieved, list L_Q_k. Precision at k is the fraction of inspected results that are relevant. Precision at cutoff k is computed as the size of the intersection between the first k results and the relevant results set, divided by k. Recall at k is the fraction of all known relevant results that the first k retrieved results contain. Recall at cutoff k is computed as the size of the intersection between the first k results and the relevant results set, divided by the size of the relevant results set. Here, vertical bars denote set size. These definitions assume binary judgments, a fixed cutoff, and a known denominator for relevant material. If no relevant chunk has been identified, recall is undefined rather than zero. Exclude that case from recall aggregation and report how many such cases exist. Retrieval identities must also be unique before scoring. The scorer consumes canonical retrieval result and CREL identities. A repository boundary adapter maps those records to stable document IDs and preserves query, document, and snapshot identity rather than inventing a competing local schema. Duplicate IDs are rejected rather than silently counted inconsistently. Suppose the service animal query has 4 relevant chunks in the version knowledge base, and an improved top 5 run contains 2 of them. Then precision at 5 is 2 divided by 5, or 0.40, and recall at 5 is 2 divided by 4, or 0.50. The retrieval stage found half of the known support, while 3 of its 5 context slots carried noise. That evidence supports widening or improving candidate retrieval. It does not yet show that the final answer will be wrong, because a downstream re-ranker might place the 2 useful chunks first, nor does it show that the 2 retrieved chunks are sufficient. Use recall to protect the candidate pool. Broad candidate retrieval should usually optimize recall before precision because its job is to avoid losing answer-bearing evidence. Missing the only clause that states an exception is a hard failure. Admitting several plausible candidates is often recoverable through re-ranking, filtering, or context assembly. For each query in the top 5 property policy experiment, record the retrieved IDs, rank, relevance labels, query text, chunking snapshot, embedding or lexical adapter version, filters, and cutoff. A configuration that raises recall at 5 from 0.50 to 0.75 may be the better first stage system, even if precision at 5 falls from 0.60 to 0.40, provided the extra noise fits the re-ranker and context budget. Conversely, high recall achieved by returning nearly the entire corpus is not useful candidate retrieval. It merely postpones the cost and ambiguity. Broad retrieval measures whether at least one adequate support path was preserved. Re-ranking measures whether the strongest support was placed high enough. Generation and citation evaluation answer different questions. Retrieval recall does not establish answer sufficiency, citation correctness, or policy compliance. Judge precision against the number of results the next component can actually consume. If a re-ranker receives 50 candidates but passes only 8 chunks to the model, precision at 50 may look poor without indicating a problem. But sending all 50 into a constrained context can introduce noise that obscures conflicts, increases latency and cost, and makes citations harder to align with claims. Report precision at operational cutoffs, such as candidate retrieval at 20 or 50, re-ranking at 5 or 8, and assemble context at its actual chunk limit. Choose the cutoff based on the number of results at the interface being evaluated, not convention alone. A top 5 score does not directly describe top 20 behavior. For a question requiring one authoritative listing-specific record, returning that record plus 4 irrelevant articles produces are at 5 of 1.00 and p of 5 of 0.20. That may be acceptable if re-ranking isolates the authoritative record, but it is dangerous if the generator treats all 5 as equally trustworthy. A neighborhood question requiring zoning, transit, and amenities may need 5 relevant chunks. One perfect hit can have precision 1.00 at 1 while still lacking coverage. Metrics must follow the evidence contract. Keep aggregate reporting from masking important differences among query groups. Compute per query scores first, then report macro averages as the arithmetic mean across queries with defined labels. Macro recall gives every query equal weight, so easy listing questions cannot mask failures on policy or neighborhood questions. A micro-style aggregate can also describe total retrieved items, but it must be labeled clearly because it weights queries differently. At minimum, slice results by question family, listing, policy, and neighborhood, and by conditions affecting retrieval difficulty. These include source type, query length, an address or date, policy version, ambiguity, and whether the answer requires one chunk or several. Include query counts, the judged relevant denominator, and unresolved or unscorable cases. A single R at 5 dashboard number does not show that every slice is safe. The Retrieval Metrics Notebook and Machine-Readable Report join each synthetic or human-authored query to its CRELs, preserve configuration hashes, emit per query and slice-level precision and recall at K, and retain missed relevant IDs for error review. This lineage lets the experiment matrix compare chunking, filters, candidate cutoffs, and re-ranking. The score belongs in the durable evaluation core. Schema conversion belongs at the repository boundary. Canonical records carry the stable query ID, source or snapshot ID, ranked result document IDs, and CREL document IDs. The adapter extracts those stable IDs from the retrieval result and CREL schemas and passes them to the metric functions without redefining the records. This adapter scores canonical retrieval and CREL records. It validates K, materializes the complete ranked input, rejects duplicate retrieved document IDs, applies the cutoff, computes precision and recall from stable document IDs, and rejects an empty relevant set for recall. The canonical record adapter first checks shared query and snapshot identity, then passes the schema fields to both metric functions. The tests cover the property policy case, duplicate IDs, identity mismatch, and invalid inputs. From future __. The adapter checks that retrieval and CREL records share a query and source snapshot, then scores the stable document identity supplied by the canonical schemas. It creates no local query, document, or CREL objects. The helper validates the complete ranked input before applying the cutoff, so duplicate IDs beyond the requested cutoff remain data quality violations. The expected output is a passing test run. The property policy fixture produces precision at 5 equals 0.40 and recall at 5 equals 0.50. Replace the shown field access with established schema accessors if their names differ. Preserve the identity checks. Run the tests in the pinned environment, and record the dependency lock file. The implementation itself has no external side effects or credentials. The evidence supports a bounded decision, whether a retrieval configuration preserves enough judge support at a specified interface and how much noise it introduces. It cannot establish that judgments are complete, chunks are sufficient, the generator will use them correctly, or unseen policies and users behave similarly. It can fail with incomplete labels, mixed source versions, mishandled duplicate identities, queries needing coordinated evidence across chunks, or relevance treated as authority. These limitations call for better judgments and targeted slices, not indiscriminate optimization. For AI engineers and product engineers, the report identifies whether to change query construction, chunking, filters, or prompts, and prevents prompt work from masking retrieval loss. Evaluation engineers maintain CRELs and slice definitions. ML platform engineers preserve snapshots and reproducibility. Safety engineers inspect sensitive policy slices and authority boundaries. The next experiment is a grid of retrieval and re-ranking configurations selected with quality, latency, and cost evidence rather than a single aggregate score. MRR and Indice G. Re-ranker A puts the correct 3-bedroom listing first. Re-ranker B puts it fourth, but places 2 other listings with the right neighborhood, price range, and availability immediately behind it. If the assistant normally uses the first listing to answer, which home should I tour, it is the safer choice. If it assembles evidence from several listings to answer, what options meet these constraints? B may be competitive or better. The practical consequence comes before the terminology. A re-ranker changes not only which documents are retrieved, but which evidence the generator sees first and which evidence may never be used. This section focuses on first hit position, when the first relevant result dominates. Let a query have a ranked list of retrieved documents. The key quantity is the rank of the first relevant document. Reciprocal rank is the inverse of the rank at which the first relevant document appears. If no relevant document is retrieved, reciprocal rank is 0. Mean reciprocal rank is the average of reciprocal rank over the queries. MRR is computed by summing each query's reciprocal rank and dividing by the number of queries. MRR gives the first relevant result all the attention. A relevant result at rank 1 contributes 1. At rank 2 contributes 0.5. At rank 4 contributes 0.25. And a query with no relevant result contributes 0. This makes MRR useful when the product experience stops at the first satisfactory answer, displays one primary listing, or passes a single best passage to a downstream component. Suppose 5 listing queries produce first relevant ranks of 1, 2, 4, no hit, and 1. Their reciprocal ranks are 1, 0.5, 0.25, 0, and 1. So MRR is 2.75 divided by 5, or 0.55. This measures how quickly one judged relevant item appears, not whether the second, third, or fifth results were useful. In the re-ranker comparison, MRR favors A if it moves the first qualifying listing from rank 4 to rank 1. That is meaningful evidence for the single listing interaction, but it is not evidence that it provides the best complete set of listings. This section focuses on graded ranking quality when several results matter. Binary relevance is often too coarse for a listing, policy, or neighborhood knowledge base. A result might be directly responsive, partially useful, merely related, or irrelevant. Assign a non-negative gain, rel_i, to the result at rank I. This section uses linear gain discounted cumulative gain. DCG at cutoff k sums each result's gain, rel_i, divided by the logarithmic discount for its rank. The logarithmic denominator discounts lower positions. The first position has weight 1, the second has weight 1 over log base 2 of 3, and so on. Fix the exact gain scale and discount before comparing systems. If labels use grade 0, 1, and 2, use those grades directly. If a different gain transformation is used, apply it consistently to both DCG and IDCG. Indice G normalizes DCG against the ideal ordering for that query. IndCG at cutoff k is DCG at cutoff k divided by ideal DCG at cutoff k. IDCG at cutoff k is the DCG obtained by sorting the query's judge gains from highest to lowest and retaining the first k. When IDCG at cutoff k is 0 because the query has no judged relevant items, exclude the query from the mean or handle it by a documented policy. Silently treating it as a perfect score would distort the result. IndCG is a graded top K ranking measure, not simply a longer version of MRR. For a query, the retrieved grades are 2, 1, and 0 at ranks 1 through 3. The displayed linear gain formula gives DSG3 approximately 2.631. The ideal ordering is 2, 1, 0, so IDSG3 is also approximately 2.631 and INDSG3 equals 1. The alternative grade ordering is 0, 2, 1. For the ordering 0, 2, 1, the displayed linear gain formula gives DSG3 approximately 1.762. The same ideal denominator, approximately 2.631, produces INDSG3 approximately 0.670. The second ranking contains the same judged evidence, but presents it poorly. These values use the displayed linear gain formula. A team using an exponential gain transformation must state that choice and recompute both DCG and IDCG consistently. For the two listing re-rankers, INDSG can reward B for placing several strong matches near the top, even if A wins on first hit position. This requires fixed graded CRELs and a fixed cutoff. The labels must say how well each listing satisfies the query, and the same K and gain mapping must be used for both re-rankers. With those controls, INDCG is the appropriate distinction when the assistant presents a short list, compares neighborhoods, or needs multiple policy passages to construct a supported response. Recall remains the boundary condition for interpreting ranking metrics. Ranking metrics cannot reward evidence that was never retrieved. A re-ranker operating on 10 candidates cannot place the 11th candidate correctly. Report MRR or INDSG alongside recall at the candidate generation boundary, and preserve the retrieval stage in the experiment record. High MRR with low recall may mean that the system finds one easy relevant item while omitting other acceptable answers. High INDCG on a narrow candidate set can likewise conceal missing neighborhoods, policy exceptions, or listing types. Consider a counterexample. The query asks for pet-friendly rentals under a specified budget near a transit station. Re-ranker A returns one excellent listing first and omits the only listing that satisfies the transit constraint. MRR may be strong if the first result is labeled relevant under a broad rubric. A graded, attribute-aware CREL could mark A's result as partial and the omitted listing as fully relevant. But no ranking metric can recover the omitted item. The remedy is candidate recall, query interpretation, or labeling, not another re-ranking prompt. For multi-document answers, an individually relevant listing may not establish availability, and a neighborhood page may describe transit without describing current inventory. Relevance, authority, sufficiency, and citation support must be judged separately. MRR and INDCG evaluate ordering against chosen relevance labels, but they do not prove that the retrieved set answers the question or that a generator will cite it correctly. Position discount and context assembly. The usual discount in DCG encodes a product assumption. Earlier results receive more attention. In RAG, that assumption may matter again when ranked chunks are concatenated into a context window. Some research and engineering observations motivate caution about lost in the middle. The possibility that information placed between the beginning and end of a long context can be used less reliably than information at salient positions. The effect depends on model, prompt structure, context length, task, and assembly method. It should be measured on the target system rather than treated as a universal law. A compact interpretation is position rank 1, rank 2, rank 3, rank 4. Straight face, straight face, straight face, straight face DCG weight $1/log_2, a +1, $1.0000.6, 310.5 over 0.431. This is a weighting convention, not a measurement of a model's private attention. If the real estate assistant places policy exceptions in the middle of a long listing context, test that assembly directly. The artifact that changes here is the Retrieval metrics notebook and its experiment matrix. Add re-ranker identity, candidate recall measurements, graded CRELs, rank cutoffs, context order, latency, and cost. The earlier CREL contract remains the source of judged relevance. This section adds rank-sensitive summaries rather than a competing schema. A deterministic scoring artifact. The following dependency-free implementation is suitable for the companion sandbox. It handles empty rankings, missing hits, cutoffs, negative gains, and the undefined ideal case explicitly. The assertions are executable tests rather than repair instructions. This code computes reciprocal rank, mean reciprocal rank, discounted cumulative gain, and normalized discounted cumulative gain. Reciprocal underscore rank scans relevance values from rank 1 and returns the inverse rank of the first relevant result, or 0.0 when none is relevant. Mean underscore reciprocal underscore rank rejects an empty rankings collection, computes reciprocal rank for each query, and divides their sum by the number of queries. DCG rejects negative gains, applies the optional cutoff, and sums each gain divided by log 2, rank plus 1. NDCG sorts the gains to form the ideal ranking, computes ideal DCG, returns none when ideal DCG is 0, and otherwise divides DCG by ideal DCG. The main block evaluates the supplied examples, checks the stated edge cases, and prints the formatted MRR and NDCG values. Read the two formatted metric lines in the output below. The reported results are MRR equal to 0.55 and NDCG at 3 equal to 0.670. For gains 0, 2, 1, the implementation computes DCG at 3 as approximately 1.762, ideal DCG at 3 as approximately 2.631, and NDCG at 3 as approximately 0.670. The assertions establish the boundaries. A ranking with no first hit score 0, empty DCG is 0, 0 ideal query is undefined rather than perfect, and an empty MRR collection is rejected because it has no denominator. Repository work includes importing the shared CREL and ranking schemas, adding these tests to the automated suite, pinning the Python version and dependencies, and running the artifact in a clean environment without credentials or external side effects. The evidence supports choosing between re-rankers for a defined interaction and judge dataset while inspecting candidate recall, latency, cost, and slices. It does not establish universal ranking quality, complete judgments, answer sufficiency, generator faithfulness, or behavior on unseen policies and users. AI engineers use the report to decide whether to change candidate generation, ranking, or context assembly. Evaluation engineers maintain graded CRELs and slices. Platform engineers preserve snapshots and reproducibility, and safety engineers inspect authority and sensitive policy slices. The next artifact is the RAG experiment matrix, where quality, latency, and cost determine the configuration rather than any single aggregate score. The next topic is chunking experiments. A listing team begins with a grid search over chunk sizes, overlaps, boundary strategies, and metadata policies. A retrieval improvement is not automatically an improvement if answer support remains unchanged, and a prompt change cannot recover evidence that was never retrieved. The team therefore rebuilds the listing index for each configuration and evaluates the same questions against every variant. The next question is what to vary and what to hold constant. Chunking is part of retrieval, not merely formatting. Small chunks can isolate a listing attribute and improve precision, but may separate a price, restriction, or neighborhood description from the evidence needed to interpret it. Large chunks preserve context but use more tokens, weaken similarity signals, and may combine unrelated listing facts. Overlap can preserve evidence across boundaries, while increasing duplicate retrieval, index size, and context cost. Compare at least 3 boundary strategies. Fixed chunking, split by a target token or character budget with a configured overlap. This is simple and reproducible, but it may cut across headings, tables, or paragraphs. Semantic chunking. Place boundaries where topic or embedding similarity changes substantially. This can preserve topical units, but its thresholds and embedding model become additional experimental variables. Document-aware chunking. Use the source structure, listing fields, policy sections, neighborhood profiles, headings, tables, and paragraphs, to preserve units that have meaning in the source. This often produces variable-sized chunks and requires explicit rules for oversized fields. Vary metadata separately from text boundaries. A minimal policy might attach only document_ID, chunk_ID, and source type. An enriched policy might add neighborhood, property type, price band, heading path, publication date, and permission or source labels. Metadata can improve filtering and interpretation, but can also leak query-relevant labels into retrieval or create inconsistent behavior when fields are missing. Treat metadata as part of the index variant, not as an unrecorded implementation detail. Hold the corpus snapshot, parser, query set, evidence-level judgments, retriever, top case settings, tokenizer, generation settings, and evaluation rubric constant. Keep filters constant as well unless the experiment explicitly tests filtering. The same listing question must encounter the same source records and judgment set in every variant. Otherwise, a score difference can reflect corpus drift or changed evaluation conditions rather than chunking. Rebuild indexes as comparable artifacts. Every variant needs a fresh index build. Record the chunking method, target size, overlap, boundary rules, metadata policy, parser identifier, dependency lock file identifier, corpus fingerprint, and index fingerprint. Keep each chunk identity stable within the build and traceable to its document, revision, ordinal, and source span. Text alone is insufficient because identical text can occur in different documents or revisions. Deduplicate retrieval measurements by stable chunk identity and report text duplicates separately. Because overlap creates near duplicate text, counting every returned chunk as independent evidence can exaggerate recall and inflate context token totals. For a listing question, overlapping chunks from the same source span are not two independently retrieved supporting units. Preserve their identities for debugging, then collapse them under the shared evidence level scoring contract before calculating support or sufficiency. The compact comparison below makes the main overlap effect explicit. This comparison makes shared boundary evidence explicit. The diagram is illustrative rather than a prescription. More overlap is useful only when it recovers boundary crossing evidence often enough to justify its duplication and cost. Measure retrieval and answer effects separately. Use the established evidence-level workflow rather than a local document-only proxy. For each query, maintain judgments that identify the supporting chunk or source span and distinguish relevant evidence from merely related text. Report candidate recall, first hit position, ranking quality, duplicate rate, retrieve token count, and a local latency proxy before evaluating generation. For the downstream answer, score support, sufficiency, relevance, and citation correctness separately. Support asks whether claims are entailed by retrieved evidence. Sufficiency asks whether the retrieved evidence covers what is needed to answer the question, including multiple required constraints. Relevance asks whether the answer addresses the question. Citation correctness asks whether each citation points to the evidence supporting its associated claim. A variant can have strong candidate recall, but poor sufficiency when it retrieves only one of several required listing constraints, or strong relevance, but weak support when the answer adds unsupported details. The listing experiment should return to the same query set after every index rebuild. For example, if a question asks for a pet-friendly 2-bedroom near a particular neighborhood, evaluate whether the retrieved evidence covers bedrooms, pet policy, and location, not merely whether one related listing was retrieved. Slice results by question type, document structure, neighborhood, and evidence count. Choose among tested variants only when improvements persist on relevant slices and remain acceptable on token use, latency, cost, and failure rates. Sandbox implementation. The companion artifact should consume the shared records, evidence-level judgments, tokenizer, index interface, and scores established earlier in the chapter. The following code shows the experiment contract. The repository adapter supplies those shared components rather than redefining incompatible toy schemas. This code runs isolated chunking variants through indexing, retrieval, answer generation, and scoring. Each variant supplies a method, token target, overlap, and metadata policy. Run_variant builds chunks and an index, searches each query for 10 hits, generates answers, and returns the variant configuration, corpus and index fingerprints, retrieval and answer scores, retrieved token totals, a latency proxy, and chunk counts. Run_grid applies that process to every variant, and the assertion checks that each report row has a distinct index fingerprint. The assertion checks that each material configuration produced a distinct recorded index artifact. It does not prove that the build is correct. Expected output is a deterministic report with one row per variant, including corpus and index fingerprints, candidate recall and ranking results, answer support and sufficiency, citation results, retrieved token totals, a local latency proxy, and chunk counts. Inspect the report by slice rather than selecting the highest aggregate score. A configuration that raises retrieval recall while lowering sufficiency or sharply increasing duplicated tokens needs investigation, not automatic adoption. In the cumulative real estate assistant, this experiment changes the chunked listing index artifact and its experiment record. It does not change the source corpus, shared evidence judgments, generation prompt, or score. The same RAG experiment matrix can then be joined with the ranking and re-ranking experiments in the next section. Limits and decision boundary. This evidence supports a decision about which tested chunking and metadata configuration performs best for the specified corpus snapshot, workload, judgments, and operational constraints. It cannot establish universal superiority, guarantee behavior on unseen documents, prove policy completeness, or replace domain review. Document-level candidate recall is only a sandbox proxy. Production evaluation should use chunk or evidence-level judgments. Local timing and illustrative fingerprints are not production claims. Fair housing, privacy, consent, representativeness, and real estate policy examples require qualified review, and LLM-Judge rationales are evaluation signals rather than proof of correctness. The daily engineering responsibility is to preserve these contracts. The AI or evaluation engineer designs slices and judgments. The ML platform engineer makes index builds reproducible, and the product or safety engineer checks whether gains survive operational and domain constraints. Tune chunk size, overlap, boundaries, and metadata empirically. Then select a configuration only when retrieval and downstream support or sufficiency evidence agree. Hybrid retrieval and re-ranking. A property policy question asks whether a landlord may impose a particular screening requirement. BM25 retrieves the policy page containing the exact phrase income verification. An embedding search retrieves a neighborhood guide that discusses affordability and a listing description that uses qualified applicants. The system combines BM25 and embedding results, retains the top 20 fused candidates, re-ranks those 20, and then passes the latter documents to the answer generator. The generator produces a fluent, plausible explanation. It is also the best answer the system could produce from the evidence it was given, and still wrong for the question. The practical consequence is immediate. A retrieval experiment must identify which stage lost the evidence. A prompt change cannot recover a policy document that was never retrieved. The cumulative real estate assistant therefore needs separate evidence for lexical retrieval, semantic retrieval, access and metadata filtering, candidate generation, and re-ranking. Its RAG experiment matrix should compare those stages rather than record only the final answer score. Give lexical and semantic search different jobs. Sparse retrieval, commonly implemented with an inverted index and a lexical scoring method, such as BM25, is strong when the query contains names, addresses, ordinance numbers, listing identifiers, or exact policy language. It can distinguish HOA from HSA, preserve unusual proper nouns, and expose a document that uses the same terminology as the user. Dense retrieval is useful when the query and document express the same idea with different words. A user asking whether pets are permitted may retrieve a document describing animal restrictions, even when the word pets is absent. Semantic similarity is not authority. However, a neighborhood overview can be close in meaning to a policy question while lacking the governing rule. The engineering choice is not sparse versus dense. It is which failure modes each method covers. For the assistant's listing, policy, and neighborhood knowledge base, run both searches, retain document identifiers and rank positions, and combine candidates before applying a learned or hosted re-ranker. Reciprocal rank fusion is a useful durable baseline because it uses rank rather than assuming that scores from different indexes are directly comparable. The implementation below imports the shared schemas, fixtures, and score used by the earlier chapter artifacts. Only the section-specific orchestration and the adapter boundary remain here, so the experiment uses the repository's established data contracts rather than redefining incompatible toy versions. This code fuses sparse and dense ranked lists without treating scores from different indexes as equal, then re-ranks a bounded candidate set. Reciprocal rank fusion validates the rank sequence and repeated document text, accumulates rank-based scores, and sorts deterministically by fused score and document ID. The experiment truncates the fused candidates, rebuilds their ranks, calls the re-ranker, asserts that policy 7 is first, and prints the resulting identifiers and scores. The expected output is policy 7 3.0, listing to 0.0. The assertion shows that retrieval systems can disagree about rank, while fusion preserves both candidates, and re-ranking promotes the document, whose wording matches the query. The 3.0 score comes from the deterministic keyword score, finding income, verification, and policy in policy 7. That score is only a test double, not evidence that lexical overlap is sufficient for production relevance. Run this example with the pinned environment and automated tests. Provider adapters, credentials, and model-specific interfaces remain outside this durable core. Start with filter checks, then investigate ranking. Filters answer a different question from relevance. A document can be relevant but outside the requested municipality, current but restricted to an internal audience, or public but not authoritative for lease rules. Test each filter in isolation with known inclusion and exclusion cases. Record whether it removed needed evidence, admitted unauthorized evidence, or only changed ordering. Apply authorization and hard scope constraints before content reaches the generation context, and test those constraints independently from sparse and dense retrieval. Otherwise, a combined score can conceal an access defect behind a strong-looking answer. For real estate examples, keep domain reviews separate for fair housing and transaction-sensitive cases. Retrieval metrics do not establish that policy interpretation is legally or operationally complete. An exact street address can be the correct lexical match, even when its embedding is less similar than a general neighborhood guide. Conversely, a paraphrase question may require dense retrieval, even when no query term appears in the governing document. Hybrid retrieval should improve coverage across these cases rather than forcing every query through the same evidence path. Assess candidate generation separately from re-ranking. Measure candidate generation by recall at the chosen cutoff. Determine whether the relevant or required evidence appears anywhere in the retrieved pool. Precision at that cutoff can describe the pool's noise, but it cannot replace recall when a missing document makes downstream support impossible. For multi-document questions, label the required evidence set instead of treating one relevant document as sufficient. Re-ranking changes the order of a candidate pool, so measure ranking quality at the context cutoff. Use graded relevance when authoritative policy, useful background, and irrelevant material should receive different treatment. Check whether re-ranking demotes an essential companion document, such as a policy exception paired with a general rule. Then connect these metrics to answer support, citation correctness, and sufficiency. A strong re-ranker score does not prove the answer is correct, and an LLM-Judge's rationale is not independent evidence of correctness. Each experiment row should retain the query slice, index fingerprint, filter decision, candidate cutoff, re-ranker version, retrieved identifiers, stage scores, answer support, citation scores, token count, latency, and cost. Measure median and tail latency when operationally relevant. Record cost using the team's actual deployment accounting, and compare re-ranking expense with improvement in supported answers rather than ranking quality alone. Extend the RAG experiment matrix with sparse-only, dense-only, hybrid, filtered, and hybrid plus re-ranker rows while preserving prior chunking and metadata settings. For each row, attach candidate recall and re-ranker at cutoff results. The concrete test combines BM25 and embeddings, retains the top 20 fuse candidates, re-ranks them, and checks whether the policy document survives filtering and context selection. The evidence supports a decision only among the tested retrieval configurations, evaluated snapshot, and workload. It can indicate whether missing evidence is more consistent with lexical vocabulary gaps, semantic mismatch, filter errors, candidate truncation, or re-ranker ordering. It cannot establish universal superiority, guarantee behavior on unseen documents, prove policy completeness, or show that a better retrieval score improves every generated answer. Index drift, incomplete labels, changing documents, adversarial queries, and domain-specific authority rules can invalidate an apparent win. The work spans several responsibilities. AI engineers design the hybrid path and inspect failures. Evaluation engineers maintain relevance labels and slices. ML platform engineers make index builds and fingerprints reproducible. Product engineers weigh latency, cost, and user value. And safety engineers test authorization, policy boundaries, and harmful retrieval paths. The result should be a reproducible experiment row that can be reviewed in CI or an operational dashboard, not merely a notebook result. Run the retrieval experiment grid and select a configuration only when candidate coverage, re-ranking quality, supported answers, latency, and cost remain acceptable on important slices. Then carry the selected context into the following sufficiency tests. Retrieval can make the right evidence available, but it cannot by itself show that the assembled context is enough. Now examine whether the selected context contains enough evidence to answer. A retrieval system may return the right kind of evidence and still produce the wrong answer if the packer supplies the wrong slice. In the real estate example, the assistant must answer whether a listing permits pets and whether a neighborhood policy allows a particular use. The retriever returns an outdated pet addendum, a current listing fact sheet, and a long neighborhood policy. The generator says pets are allowed because that is the clearest statement in context, even though the current listing says no dogs. Given the selected documents, that answer may be the best possible generation. The failure occurred during context assembly. The practical question is not simply whether retrieval worked. It is whether the selected context contains enough usable, current, non-conflicting evidence to answer the request, while preserving where each claim came from. This is a packing and evaluation problem rather than a prompt writing problem. Sufficiency is a distinct retrieval outcome. Relevance asks whether a retrieved item concerns the query. Sufficiency asks whether the assembled items cover the evidence needed for a defensible answer. For example, a listing that mentions a fence yard may be relevant to outdoor space, but insufficient to determine whether dogs are permitted. That answer may also require the animal policy, a building rule, and a date or version marker. Create an evidence checklist for each evaluation question. For the question of whether a tenant can keep a dog at 17 Cedar Lane, the checklist might require the evidence needed to consider the answer supported. The checklist includes 4 needs. A property-specific animal rule must come from the listing or property record. Otherwise, a neighborhood policy may be generalized incorrectly. A building or lease restriction must come from the current building policy. Otherwise, the listing may be incomplete. Any applicable exception or approval process must come from the policy source. Otherwise, a conditional answer may become unconditional. Finally, an effective date or version from source metadata is needed so stale evidence is not treated as current. Represent evidence needs as named requirements rather than broad categories. Property_animal_rule, building_restriction, approval_process, and effective_version. Each requirement is evaluated independently. A building policy document may satisfy building_restriction while failing approval_process if it contains no approval procedure. This prevents category-level presence checks from falsely labeling the context sufficient. Score sufficiency against the evidence needs, not the number of chunks. 6 redundant listing descriptions may be less sufficient than 1 listing record combined with the applicable policy and its effective date. The sufficiency record should state which requirements were met, which were missing, and whether conflicts remained unresolved. A judge's rationale can help locate a problem, but is not proof of correctness or a substitute for source-based review. In the cumulative assistant, this changes the artifact produced after hybrid retrieval and re-ranking. The retrieval experiment row is extended with a context pack record containing the query ID, selected source IDs, source versions, token or character budget, evidence requirements, source IDs mapped to each requirement, coverage status, conflicts, truncation events, and citation spans. Generation can then be evaluated against a known context state rather than an opaque prompt. The priority here is coverage rather than fluency. Packing is an allocation decision. Reserve space for the evidence categories that answer the question, then fill remaining capacity with supporting context. Do not let a verbose policy consume the budget before the listing facts have been included. Conversely, do not always place listing facts first. A policy exception may determine how those facts must be interpreted. A useful deterministic order for the scenario is: use this order. First, current, property-specific facts. Second, binding building or lease policies. Third, neighborhood rules that apply to the request. Fourth, exceptions, definitions, and approval procedures. And fifth, lower priority explanatory or historical material. Within each category, prefer authoritative and current sources, then preserve the source boundary and a compact citation anchor. The packer should record every excluded item and every truncated source. Silent truncation is an evaluation failure because it makes an apparently retrieved fact indistinguishable from an unavailable fact. Redundancy deserves its own test. 2 copies of the same listing text may crowd out a policy exception without increasing evidence coverage. Measure duplicate or near duplicate content by source identity and normalize claims, but do not deduplicate away genuinely independent confirmations. Ordering also deserves a test. Run the same evidence set in alternate orders when a model or serving stack is sensitive to position. A result that changes when a policy moves below a long listing description is a context ordering defect, even if retrieval metrics are unchanged. Conflicts must remain visible. If the listing says pets allowed and the current lease policy says dogs require written approval, the pack must retain both sources, identify the contradiction, and direct the answer toward a conditional response or abstention. Overriding one source with another hides the very case the evaluator needs to inspect. Conflict rules should be supplied as explicit, versioned comparison inputs rather than hidden in a one-off conditional, so domain reviewers can extend them and inspect why a conflict was recorded. The next section specifies the deterministic packing process and its evidence record. The reference implementation uses plain Python data classes and local fixtures. Its schemas should align with shared evaluation records and remain pinned in the repository lock file. Provider-specific tokenizers belong in an adapter, not in the durable record format. The pack_context function deterministically packs local evidence and reports requirement level coverage. Evidence is ordered by descending priority and then source ID. Items are omitted when they add no novel claim or when the budget is exhausted. Selected items consume bounded word units, and oversized items are marked truncated. The record tracks selected, omitted, and truncated sources, requirement to source mappings, covered and missing requirements, used units, and conflicts. The main fixture checks that all three sources are selected, no requirements are missing, the requirement mappings are correct, the claims conflict is preserved, and the JSON output contains the context and record. The contract records deterministic ordering, source and version markers, bounded packing, omission and truncation records, requirement level coverage, and conflicts. Under the stated budget, all three fixture records fit, every named requirement is covered, and the neighborhood item remains selected even though it is not required. The direct contradictory claims remain visible as a pair rather than one source replacing the other. With a smaller budget, the neighborhood source would be recorded as omitted or truncated. Word units make the artifact reproducible without a provider-specific tokenizer. Production hardening should replace the estimator with a pinned tokenizer adapter, enforce source and total budgets, preserve stable document hashes, normalize or escape untrusted source text, and test duplicate claims, Unicode, empty documents, conflicting versions, and truncation at citation boundaries. Conflict pairs should come from a reviewed policy or claim comparison layer, and the implementation should consume shared repository schemas rather than creating a parallel contract. All inputs here are local synthetic fixtures, so consequential tools are unnecessary. The dates must not be interpreted as current real estate records. The boundary case, relevant but not sufficient. For a school district transfer question, 3 neighborhood pages about nearby schools can all be relevant while stating none of the eligibility rule, required residence documentation, or applicable date. Relevance can improve, while sufficiency for the requested decision remains 0. The evaluator must label the missing evidence explicitly instead of rewarding topical similarity. The context packing test suite should cover property, policy, and neighborhood slices, current and stale source pairs, contradictory claims, long policies that force truncation, duplicate listing chunks, and questions whose correct answer is insufficient information. The resulting artifact is a bounded evidence packet plus a requirement level sufficiency record, which generation and citation tests consume next. This evidence supports a specific decision, whether the packing strategy and budget preserve named evidence requirements for the tested workload with acceptable latency and cost. It can identify redundancy, ordering sensitivity, source conflicts, and missing or truncated evidence. It cannot prove that the generator will use every included fact, establish sufficiency for unseen questions, resolve an underlying policy dispute, or prove citation correctness merely because a citation points to a selected source. Labels, authority, effective dates, token estimates, and conflict rules may be incomplete or ambiguous, and compact context can still fail under adversarial or multi-turn queries. AI engineers inspect the packer. Evaluation engineers maintain evidence requirements and reviewed conflict cases. ML platform engineers version indexes, documents, and tokenization adapters. Product engineers compare quality with latency and cost, and safety engineers test stale, unauthorized, or policy-sensitive evidence paths. The daily handoff is a reproducible context record, not a prompt screenshot. Run experiments that vary packing strategy, budget, and ordering. Choose a configuration only when retrieved evidence is available, sufficient context is demonstrated, and conflict handling, citation preservation, answer quality, latency, and cost are acceptable on important slices. Generation evaluation focuses on whether answers are supported by the supplied evidence, relevant to the request, and appropriately uncertain or abstaining when the evidence is insufficient. In the real estate example, the retrieved listing supports the claim that the property isn't a two-bedroom building, but the claim that buyers can deduct the property's local transfer tax from federal income tax is not supported by the context and may be wrong or depend on facts outside the assistance scope. Fluency and direct phrasing do not make that second claim safe. Evaluate 3 separate properties. Each material claim must be grounded in the supplied evidence. The answer must address the user's question rather than merely repeat retrieved text, and the answer must state uncertainty or abstain when the evidence cannot support a conclusion. These tests evaluate the answer enabled by the retrieval pipeline, not an imagined answer based on the entire knowledge base. Decompose the answer into claims first, because each claim will be evaluated independently rather than treating whole sentences as the evaluation unit. Treat an answer as a set of atomic or near-atomic claims, each small enough to receive an independent support label. The example below shows how to split the response into claims. This is one independently evaluable claim from the answer. This is a claim that buyers may deduct the property's local transfer tax from federal income tax. The property claim is supported if the listing says the property has 2 bedrooms. The tax deduction claim is unsupported when no tax document entails it. Support does not transfer merely because both claims appear in one sentence or because the listing is authoritative about property attributes. Claim decomposition is partly linguistic and partly operational. Numbers, dates, eligibility conditions, negations, comparisons, recommendations, and causal statements usually deserve separate claims. A sentence combining walkability with an assertion of no flood risk joins a subjective characterization to a high-consequence factual assertion. Splitting them prevents partial support for the stronger claim merely because the weaker one is true. The companion artifact extracts simple declarative clauses, compares their normalized terms with a context sentence supplying evidence, reports that sentence as a candidate evidence span, and applies an explicit narrow contradiction rule. It is not by itself a semantic evaluator of groundedness, relevance, or uncertainty. Its role is to make claim-level data contracts and obvious support states testable. In production, reviewed annotations should define claims, evidence spans, support labels, materiality, expected aspects, and acceptable abstentions. A separately versioned human or judge-assisted evaluator can score semantic entailment, relevance, completeness, and abstention against those annotations. The durable contract is the reviewed claim record, not a particular heuristic or model. Test whether the available context entails the claim. For each claim, inspect the exact context applied to generation. Use supported only when that context entails the claim, contradicted when it conflicts with the claim, and unsupported when it is silent or insufficient. Keep these labels distinct. A missing tax rule does not show that the deduction is false. It shows that the answer should not assert it. A judge may use lexical checks, rules, a trained classifier, or another language model, but its rationale is not proof of correctness or a substitute for the cited source. Store evidence spans, the support label, evaluator version, and adjudication status, so reviewers can inspect the basis for a score. The property claim is supported with a candidate listing span, while the deduction claim is unsupported without an evidence span. If the user asked for a tax conclusion that the available context cannot establish, explicitly stating that the tax treatment cannot be determined from the listing and advising consultation with the applicable tax authority is an appropriate boundary response. The deterministic artifact marks a claim as contradicted only when the evidence contains an explicit polarity conflict, such as allowing pets versus not allowing pets. Missing information is not contradiction, and the evaluator does not determine whether a tax proposition is legally false. A stronger evaluator must address paraphrase, modality, numbers, dates, and conflicting sources explicitly rather than relying on token overlap as entailment. Support reports should distinguish material from non-material claims. An unsupported adjective, such as charming, may affect style without affecting the decision, while unsupported claims about tax, flood exposure, zoning, financing, or legal eligibility are material. The dataset and rubric should define this classification instead of leaving it to inconsistent judgment during each run. Now separate these two evaluation dimensions. Support alone does not show that an answer addressed the question. For a question about whether a listing allows pets and its monthly fee, a grounded description of the bedrooms is irrelevant. Relevance is measured against the user's requested intents, constraints, and entities. Completeness is measured against the material sub-questions the answer was expected to cover. A test case should contain a question, expected aspects, risk labels, and acceptable abstention conditions. These dimensions must be scored separately. Claim support against annotated evidence, relevance against requested intents and entities, completeness against expected aspects, and abstention against the documented sufficiency threshold. An answer may be relevant but omit the fee, or cover every aspect with invented details and remain unsupported. Lexical smoke tests can suggest spans and obvious labels, but they cannot determine these semantic scores by themselves. The same distinction applies to policy questions. If the user asks whether a showing requires an appointment, the policy document may answer it directly, while a neighborhood guide cannot fill that evidentiary gap. Retrieval relevance is not authority, and a highly similar passage is not necessarily sufficient evidence for the decision. Next, consider when declining is appropriate. A blanket refusal is safe but unresponsive when the documents support part of the answer. A targeted response states the supported fact, identifies what evidence is missing, and limits the uncertainty. For example, it can report the 2 bedrooms while stating that the provided documents do not establish the federal tax treatment of a local transfer tax. Score abstention against the reviewed test case, not against a blanket preference for refusal. Mark it appropriate when the answer declines only the unsupported or insufficiently evidenced aspect while answering supported aspects. Mark it inappropriate when supplied authoritative context answers the question, but the response refuses, or when it asserts a conclusion despite an abstention condition. Retain the question, expected aspects, evidence sufficiency annotation, response, and reviewer or judge decision. If the context says, tax treatment varies by jurisdiction and buyer circumstances, the assistant should not abstain from every tax-related question. It can report that limitation while declining to calculate or guarantee a deduction. If a current, authoritative tax policy document explicitly answers the narrow question, blanket abstention is an avoidable relevance failure. Judge abstention against evidence sufficiency and question scope. The artifact and the engineering decision. Add a generation evaluation record beside the context record. It contains the question, answer, extracted claims, support labels, evidence bands, expected aspects, answered aspects, relevance and completeness scores or annotations, abstention status, evaluator versions, and review outcome. The artifact records what the answer asserted and which packed evidence supports each assertion. Citation tests can consume these claim-to-span links rather than reconstructing them from prose. The Python artifact is a deterministic smoke test for this contract, not a tax evaluator and not a legal determination. Using local strings, it demonstrates claim extraction in a structured support judge without credentials or external side effects. It verifies three mechanical states: supported, contradicted with explicit opposing evidence, and unsupported when evidence is absent. Reviewed annotations or a separate human or judge evaluation path must score semantic support, relevance, completeness, and appropriate abstention. Evaluation engineers maintain claim-level datasets, expected aspects, abstention conditions, adjudication queues, and release gates. ML platform engineers version the evaluator and fixtures, expose the record format in CI, and preserve reproducible runs. Product engineers decide which omissions are unacceptable for a user workflow. Safety engineers set materiality and abstention thresholds for high-consequence claims. These are daily ownership responsibilities for the artifact, not substitutes for the measurements. This section uses a standalone compatibility adapter because no shared schema import path is supplied in the brief. The adapter serializes the durable fields claim, label, evidence_span, and reason, allowing a repository implementation to replace claim result with the established chapter schema without changing the judge contract. In the companion repository, the import should change to the canonical shared schema, reviewed fixtures, and scores. The local smoke test does not redefine that repository contract. This Python smoke test extracts answer claims and judges each against context sentences as supported, contradicted, or unsupported. It validates non-empty answer and context inputs, normalizes tokens, detects explicit polarity conflicts, and links supported or contradicted claims to evidence spans. The example then prints structured claim results and asserts the three expected labels and evidence span outcomes. The expected labels are supported, contradicted, and unsupported. Matching claim wording can pass normalization, but contradiction requires explicit opposing context, and merely omitting a topic leaves the claim unsupported. These states test the mechanical contract without establishing legal or tax correctness. This baseline still has limits. It can overcredit unrelated shared words, misparaphrases, mishandle scope or numerical changes, and select terms without true entailment. Evidence spans remain candidates for review. Hardening requires stronger claim segmentation, explicit span entailment, negation and numerical tests, calibrated evaluators, adversarial tests, version prompts or models where applicable, human adjudication for high-risk claims, clean environment execution with pin dependencies, and automated tests. Reviewed annotations remain the reference, while model judges may accelerate but not replace adjudication for consequential claims. Provider adapters belong outside the durable record format, and earlier canonical schemas, fixtures, or scores should be reused when available. These measurements support a bounded decision about whether a generator configuration is sufficiently grounded, relevant, complete, and appropriately uncertain for tested slices. They do not prove truth beyond supplied sources, guarantee unseen question behavior, resolve conflicting policies, or establish legal or tax advice. They can also fail when claims are merged, context is stale, paraphrases are missed, or an answer is misleading through omission. Compare configurations using the experiment grid, including latency and cost. Ship the cumulative real estate assistant only when reviewed material claim support, relevance, completeness, and abstention meet agreed gates. Do not hide an unsupported tax claim behind a fluent aggregate or lexical score. This section focuses on whether citations are correct and complete. A neighborhood comparison can resolve all 3 citations and still be unsafe. One source may describe the wrong neighborhood, another may use a different year, and none may address flood risk. Evaluation must inspect the relationship between each individual claim and its evidence rather than simply count citation markers. Begin by examining the citation object rather than the answer score. For each answer, preserve the answer text, atomic claims, citation identifiers, retrieved chunks, source metadata, and an accessibility result. A citation exists only when its identifier maps to a known source record. It is accessible only when the evaluator can retrieve or inspect the reference content under the intended user conditions. Missing chunks, expired URLs, and inaccessible documents fail existence or accessibility even when their prose appears plausible. In the cumulative real estate assistant, an indexed listing may be absent from the citation payload. An internal policy may be unavailable to the user, and an outdated neighborhood profile may remain resolvable. Record the source ID, document version, or timestamp when available, displayed locator, accessibility status, and the exact retrieved text used for adjudication. Evaluate citation correctness claim by claim, not only at the level of whole answers. Split the answer into material assertions before scoring it. Maplewood is cheaper and has shorter commutes, contains at least 2 claims, and may require different evidence. For each claim, check whether the cited passage supports it as written, including its subject, time period, comparison direction, quantity, qualification, and scope. A passage saying Maplewood's median asking price was lower in 1/4 does not entail that it is always cheaper, and a passage describing transit access does not entail a specific commute time. Record a conservative outcome for each claim: supported, contradicted, insufficient, or not applicable. Insufficient means the supplied citation does not establish the claim. It is not a finding that the claim is false. Automated judges can triage paraphrases and identify candidate evidence spans, but their rationales are not proof of correctness or observable private reasoning. Numerical, temporal, negated, and high-consequence claims deserve deterministic checks or human review where feasible. For comparison, support the price claim only when the cited records contain comparable price definitions and a valid comparison. A listing time claim fails when its citation reports a different period without an explicit qualification. A flood risk claim is unsupported when no cited policy, hazard record, or neighborhood source addresses it. Remove the claim, qualify it, or abstain instead of attaching the nearest looking citation. Measure whether material claims have adequate support rather than counting citations. Citation precision asks whether citations attached to claims actually support them. Citation coverage asks whether material externally verifiable claims have adequate support at all. Let C be the set of material claims. Let SC indicate that claim C has at least one accessible citation that entails it, and let WC be its importance weight. Weighted citation coverage uses these quantities. Weighted citation coverage is the sum of the importance weights for claims with entailing citations, divided by the sum of the importance weights for all material claims. SC equals 1 only when the claim passes the existence, accessibility, and entailment checks. Otherwise, it is 0. If all claims have equal weight, coverage is the fraction of material claims supported. Citation precision can be defined over citation attachments. If A is the set of citation to claim attachments and indicates that attachment entails the claim it accompanies, those attachments provide the basis for measuring precision. This defines precision as the sum of entailment results A across claim attachments in A, divided by the number of attachments A. With 4 claim attachments and 3 genuine entailments, precision is 3 divided by 4 is equal to 0.75. With 5 equally weighted material claims and 3 supported, coverage is 3 divided by 5 is equal to 0.60. These measures need not improve together. Weights should be agreed before looking at results. A transaction policy restriction or safety qualification may deserve more weight than a descriptive adjective. Do not hide missing support by averaging it with many trivial claims. We now examine decorative citations and how to detect them. A decorative citation does not support the proposition the reader is likely to associate with it. Warning signs include one citation attached to a paragraph with several claims, a source that merely repeats the question, a broad neighborhood page used for a precise statistic, or a citation included only because Retrieval returned it. For the Maplewood, Riverton audit, record each atomic claim, cited chunk IDs, accessibility result, entailment label, and failure reason. This reveals the unsupported flood risk assertion and supports regeneration with that claim removed or with retrieval targeted at an appropriate hazard source. The citation audit record and scorer feed into the RAG experiment matrix. The next implementation uses a deterministic audit record. The adapter imports the established chunk and source schemas and converts them to the displayed fields. The scorer does not redefine those shared schemas. The local standard library only fixture runs without credentials or external side effects. It preserves source ID, version or timestamp, locator, existence, accessibility, and exact evidence text, emits attachment level results, and computes precision and weighted coverage. The entailment function is a conservative fixture scorer rather than a semantic truth engine. It checks explicit facets, subject, comparison, numeric value, and temporal qualifier. Valid paraphrases, unrecognized negations, and conflicting sources remain unresolved and receive no credit. Production systems should augment this boundary with evidence spans, numerical and temporal validation, calibrated evaluators, and human adjudication. This code audits whether cited source records exist, are accessible, and support claims under explicit fixture rules. It represents sources, claims, and attachment results as immutable records, extracts recognized facets, marks unsupported cases unresolved, and computes citation precision and weighted citation coverage. Missing citations become explicit rows. Inaccessible sources cannot support claims, and the public report returns the summary metrics followed by attachment records. The assertions verify precision of 0.2, coverage of 2/6, and the expected missing, inaccessible, and unresolved cases. The expected first 2 lines are equivalent to the citation precision and citation coverage records produced by the audit. The audit reports citation precision as 0.2, with a 0 attachment policy of 0.0, and weighted citation coverage as 1/3, with a 0 claim weight policy of 0.0. There are 5 attachments, 1 supported price attachment, and 4 unresolved, inaccessible, or missing attachments, so precision is 1/5, or 0.20. Only the price claim contributes to coverage. The total claim weight is 6, so weighted coverage is 2/6, approximately 0.33. Missing citation IDs remain explicit rows. Precision with no attachments and coverage with no claim weight are both reported as 0.0. These are reporting conventions, not mathematical truths, and should remain fixed across experiments. The Q1 source does not support a Q2 claim, even when it contains a related number. An inaccessible hazard record does not support a claim, and a missing identifier is reported as non-existent. A negated flood risk claim remains unresolved rather than being inferred from the absence of a hazard phrase. A valid paraphrase also remains unresolved under this narrow score and must go to a stronger evaluator or human review. Conflicting passages should remain separate evidence rows and be adjudicated as unresolved or contradicted by policy. The assertion makes the artifact deterministic for repository tests, while the adapter boundary preserves continuity with shared schemas and fixtures. The example checks whether an authorized source record provides explicit evidence under conservative rules. It does not establish that a claim is true in the world. Production hardening includes robust claim segmentation, source version checks, evidence span matching, negation and number handling, access control testing, calibrated evaluation, adversarial cases, and human review for consequential claims. Provider-specific adapters should remain outside the durable record format, and the example should run with pinned dependencies and automated tests. The method fails when claims are compound, paraphrases are not represented by the fixture facets, sources contain conflicting passages, or retrieved documents are stale. It cannot decide whether an omitted claim should have been stated, whether a source is authoritative, or whether a legally sensitive conclusion is appropriate. Its bounded decision is whether attested RAG configuration attaches existing, accessible, claim-entailing citations with sufficient coverage for defined evaluation slices. It does not prove world truth, guarantee unseen query behavior, or replace domain review. That boundary can reject unsupported neighborhood comparisons and pass a candidate onward only when quality, latency, and cost evidence remain acceptable. For AI and evaluation engineers, the regression surface checks citation precision and coverage separately as chunking, re-ranking, and prompt changes are introduced. Platform engineers can monitor missing or inaccessible source IDs. Product engineers can enforce a display contract, and safety engineers can route high-weight unsupported claims to review. The responsibility is to preserve an auditable path from each material claim to accessible evidence and make failures visible. Operationally, decompose every material comparison into claims, link each claim to accessible evidence, and test every attachment for entailment. Track citation precision and coverage independently, flag decorative citations, and use the audit record rather than fluency to select the next RAG configuration to test. The task is to select the RAG configuration. In the flood risk example, the retriever supplied outdated neighborhood guides and a general insurance explainer, while the current policy document was absent from context. That retrieval defect explains why the fluent answer was understandable from the available documents, although generation time abstention or a support check could still have prevented the unsupported answer. A larger model or rewritten prompt would hide the actual problem. The decision is not simply which RAG system has the highest answer score. Choose the configuration that provides the right evidence, assembles it reliably, produces supported answers, and remains within the product's latency and cost limits. This is a multi-objective decision based on component-level and end-to-end evidence. The evaluation compares 3 candidates before making one configuration decision. The real estate assistant team evaluates 3 variants against a shared version query set and document snapshot. Variant A is the baseline. It uses moderate fixed chunks, dense retrieval, and no re-ranker. It is inexpensive and fast, but it often mixes listing facts with general neighborhood material. Candidate B uses smaller structure-aware chunks and a hybrid retriever. It improves discovery of exact policy and listing fields at the cost of more retrieval work. Candidate C starts with B's hybrid candidates, applies a cross-encoder-style re-ranking stage, and assembles compact context. It is the slowest and most expensive candidate, but may reduce distracting evidence. These are configuration identifiers, not vendor or model claims. The experiment records chunking rules, the index snapshot, retriever settings, re-ranker version, context budget, generation adapter, prompt contract, component metrics, slices, uncertainty fields, and evidence links. Measure retrieval first. Whether the expected document or chunk was retrieved, its rank, and whether the passage is sufficiently complete. Discovery failure, poor rank, and incomplete boundaries are different failures. Then measure generation and citation separately. Given fixed context, score correctness and support. Given the answer, score whether material claims have accessible, claim-entailing citations. A citation cannot rescue a missing document, and a retrieved document does not prove the model used it correctly. For sensitive flood risk or policy questions, permit abstention or qualified domain review rather than implying a legal or safety conclusion from the evaluator score. Measure retrieval, re-ranking, context assembly, generation, and total wall clock latency independently. Record costs through the repository's accounting adapter rather than embedding volatile provider prices. A candidate that improves quality by consuming the entire latency budget is not automatically the production choice. Compare cases, not just averages. Aggregate scores can hide important failures. Pair similar tasks that differ in evidence structure. A listing question with one authoritative field, a policy question requiring an exception clause, and a neighborhood comparison requiring several dated sources. Inspect slices such as listing facts, policy constraints, neighborhood comparisons, long context questions, and queries with no sufficient answer. In the flood risk case, it retrieves a general preparedness article and misses the listing disclosure. B retrieves the disclosure but truncates the exception paragraph. C retrieves both and places the exception first. Component inspection identifies the remedy, retrieval or indexing for A, and chunking or context assembly for B, rather than a prompt change. Because the case may involve safety-sensitive policy interpretation, production behavior should abstain or route it for qualified review when authority or freshness is unresolved. A small, well-structured listing may already be answered perfectly by A, while C adds latency without changing the result. With contradictory policy versions, more context may be less safe and less freshness and authority are represented in ranking, and the assistant can abstain. More context is not universally better. Do not optimize one aggregate metric. High recall may coexist with poor context precision, high answer accuracy with unsupported claims in a critical slice, and low latency with premature truncation. Treat maximum latency, minimum citation coverage, and zero tolerance for unsupported sensitive policy conclusions as gates. Among candidates that pass, compare quality, latency, and cost. The Pareto frontier contains configurations for which no other candidate is at least as good on every objective and strictly better on one. Record the decision. The experiment matrix has one row per configuration and slice. It links retrieval judgments, generated outputs, citation audits, latency traces, cost records, snapshot identifiers, and raw evidence. The deployment decision record names the selected configuration, rejected alternatives, the slices that drove the choice, uncertainty, hard gates, the rollback target, and observable rollback triggers. This is not an informal leaderboard. The cumulative artifact is the versioned RAG configuration registry and deployment manifest for the real estate assistant. It records the retriever, chunker, re-ranker, context budget, generation adapter, document and index snapshots, constraints, rollback target, and evaluation links. provider-specific adapters, and volatile pricing remain outside the durable core. The artifact uses the confirmed shared package namespace, rag_evaluation.contracts and rag_evaluation.fixtures. Those imports must resolve from the repository root under the pinned lock file. The code does not redefine the shared results schema or fixtures. The complete supplied code block computes dominance, filters results through hard gates, derives the Pareto frontier, and builds a selection memo. The dominance phase compares quality and citation coverage as higher is better objectives and latency and cost as lower is better objectives. It requires no worse performance on every objective and strictly better performance on one. Lines 8 to 24. The frontier phase rejects empty input and invalid quality, coverage, latency, or cost ranges, then removes dominated configurations. Lines 26 to 38. The gate phase requires latency within the maximum, citation coverage at least the minimum, and zero unsupported sensitive claims. Lines 45 to 46. The memo phase requires an evaluated rollback configuration, selects eligible results, lists frontier metrics, slices, snapshots, and evidence, and records the deployment choice and rollback triggers. Lines 52 to 63. The main routine loads 3 variant results, creates the memo with B focused as the rollback configuration, checks the expected frontier and a fired rollback trigger, and prints the report. Lines 70 to 85. The shared experiment result contract carries configuration identifiers, component metrics, meaningful slices, hard constraints, uncertainty fields, document and index snapshot identifiers, raw record references, rollback triggers, and evidence links. The local code implements only this section's Pareto and memo behavior. The full test suite must cover empty input, invalid ranges, dominated candidates, each hard gate failure, mismatched snapshots, and fired rollback triggers. The pinned deterministic fixture produces the expected experiment output that follows. This experiment matrix compares 3 variants across 3 shared slices and records quality, coverage, latency, cost, a common snapshot, and linked evidence. It then states the deployment decision, rollback configuration, and rollback triggers. The output shows all 3 configurations on the frontier because each trades quality and citation coverage against latency and cost. The frontier does not choose the production winner by itself. Hard constraints, uncertainty, product requirements, and domain review determine that choice. The deployment manifest preserves the prior known good configuration as the rollback target. If C's re-ranker becomes unstable, citation coverage falls below its reviewed threshold, or latency exceeds budget, the manifest can restore B. This evidence supports a bounded decision about which tested configuration best fits declared quality, citation, latency, and cost constraints on the evaluated slices. It cannot establish performance on unseen queries, prove corpus completeness or freshness, resolve contradictory policy without domain judgment, or establish world truth from an evaluator score. Synthetic cases may underrepresent difficult language and distribution shifts. Legal, safety, and real estate examples require qualified review. Evaluation engineers maintain judgments and slices. AI engineers diagnose retrieval, ranking, assembly, and generation. Platform engineers preserve version traces and cost measurements. Product engineers enforce latency and display contracts. Safety and domain reviewers define sensitive question gates. RAG evaluation succeeds when missing evidence, poor ranking, bad context assembly, and unsupported generation are measured separately. Selection comes only after those failures are visible alongside end-to-end quality, latency, and cost, with the reasons, locations, and assumptions recorded.